So last time we learned about the knowledge distillation technique, right? So as I mentioned, the only remaining thing, because if we use the PyTorch code, the network definition becomes quite simple, right? And anyways, we can change the structure of the network by manipulating this code. And for training, we can also change the loss function, right? And also we can change the optimizer, okay? Loss function and optimizer, we can change it, but the actual learning process, we cannot change much. The remaining thing is how we can load the data set, the X and Y pairs, okay? And for sometimes we cannot secure much data because collecting X and Y, their label Y is not that easy for some cases, okay? So for that kind of situation, we can use some pre-trained teacher network to teach the student network, okay? That kind of approach can be, is called as the knowledge distillation, okay? And also in the last part, I mentioned about the pseudo labeling, okay? And this is also similar to the knowledge distillation. So actually here, there are two types of data, the labeled data and unlabeled data, okay? Our aim is to use both, okay? Labeled means they have both X and Y pairs, okay? Input image X and their corresponding label Y, we have it. But for unlabeled data, we only have X, okay? And we somehow have to obtain this Y using some maybe pre-trained network, okay? And we will call that Y as pseudo label, okay? It is not hand labeled, but it is obtained from some pre-trained network, okay? So in that sense, this pseudo is meaning some fake, okay? It is label which is relatively accurate and easy to obtain, but sometimes it could be wrong, right? So in that sense, we call it as pseudo label, okay? Yeah. So pseudo labels are target classes for unlabeled data, which is predicted from another network, okay? And we use it as if it is the true label, okay? So our aim here is using this labeled data and also the unlabeled data X and getting some pseudo labels using another network and using these two types of data to train the new network, okay? That is the concept of pseudo labeling, okay? So here again, we can see the concept of teacher and student, okay? So this U is meaning unlabeled data's input, and this head YU is meaning the pseudo label for unlabeled images, okay? So we are using both unlabeled and labeled data, okay? For the labeled data, we can safely train the student network as if we train the teacher network, okay? And for the unlabeled data, we do this, okay? This is indicating that this is the cross entropy loss. And this is the labels obtained from the teacher network, okay? And this is the output obtained from the student network, okay? We regard this as ground truth, pseudo ground truth, and train the student response, okay? Similarly to train the teacher network, okay? So we can just regard these pseudo labels as the true label during the training, okay? So one interesting fact regarding this pseudo labeling is actually reported in this paper in CVPR 20. So we call the training with pseudo labels sometimes as the self-training, okay? Because we actually need only the images input itself, and when the images, the input is secured, that we can train the network by making some pseudo labels by ourselves. In that sense, this training is called as self-training. Okay. And what they do in self-training, and actually what they insist in this paper is, they first train the teacher network with labeled data, okay? The XY pairs, using XY pairs, they first train the teacher model, okay? And infer the pseudo labels for unlabeled data, okay? And then we will train the student network, okay? We will train the student network here, okay? But I mean, here for XU, we get head YU, and this is the pseudo label, right? But when training the student network, we will add some noise for this X, the unlabeled images, okay? Using some data augmentation and some random variation, giving some random variations to the noise, to the images, we can add some noise to the input image, okay? By fixing the pseudo label, we can give some noise to the input, okay? While training the student network using this unlabeled data, okay? And then we make the trained student network as the new teacher network, okay? If we iteratively do this, so this is quite simple method, right? We first train the teacher network using the paired data, and for unlabeled data, we obtain the pseudo labels using the pre-trained teacher network, and then train the student network by inputting some noise in the unlabeled input, okay? Then this student network may have the ability to maybe denoising the input. And even for noised input, they can predict corresponding labels better than the teacher network, maybe, yeah. So because of that, if we make the student network as the new teacher and iterate these things few times, then they are saying that this is the noise student graph. The red is indicating the noise student, and the blue one is denoting the original network, okay? So the y-axis, they are denoting the accuracy, okay? So the red, the student are even better than the original teacher network, okay? So this is indicating the same thing, learning teacher with the labeled image, and use the unnoised teacher model to generate the pseudo label. And third, we use the same network structure or even larger model for the student model and train it using the labeled and unlabeled data with the noise added, okay? And then do this multiple times iteratively. Then we can get even better student model than the original teacher model, okay? So this is the self-training, okay? This is quite interesting. And the noise, they propose to add is this kind of simple noise that was used for the data augmentation. Okay, so maybe manipulating the magnitude and also the shear, applying some shear transformation and applying some contrastive things. Okay, that kind of noise we can add during the training for the unlabeled images. Okay, and then the student model is trained to process the diverse images. Okay, so it even performs better than the original teacher model. Okay, this is quite interesting result. And also for pseudo labeling, the problem is the pseudo label. As I mentioned, this is the fake data, right? Their Y value could be wrong. Okay, their annotations could be wrong. Okay, because they are predicted from the network. So the network prediction that could be wrong. Okay, so in CVPR 21, some method called as meta pseudo labels, they are proposed. Okay, so previously in pseudo labeling, there's only pre-trained. There are two networks: pre-trained teacher and student, and we made the pseudo labels using the pre-trained teacher to train the student using this additional data set. Okay, but in meta pseudo labeling method, they have another stream to train the teacher network as well. Okay, previously the teacher was fixed. Okay, and only students are trained using the additional unlabeled data. Okay, but here what they do is they actually also train the teacher network. Okay, because the pseudo labels could be wrong. Okay, they manipulate the teacher's parameter to correct the wrong pseudo labels. Okay, so this concept could become bad if the pseudo labels are inaccurate, and often the pseudo labels are inaccurate. Okay, so they propose some systematic mechanism for the teacher to correct the wrong pseudo labels. Okay, what they do is they actually determine this is the teacher weight, okay, the parameter, okay, and this is the student's weight parameters, okay. So I mean, this LU is the cross entropy loss, okay, for the students network, okay, and I mean, this is indicating that for the fixed pseudo labels obtained from the teacher network's weight, they find the optimal student model once, okay? And then for that parameters, they add another loss function that can minimize, anyway, they define another loss function for the teacher network, and they will find the teacher's weight that can minimize that loss function. Okay, so this LL is the loss function for the teacher, and this LU is the loss function for the student. Okay, this is happened for pseudo labeling, right? Using some pseudo labels from the teacher network, they apply this to train the student parameters, okay? And for optimal parameters, they again learn teachers parameters, okay, using some loss function, okay? That's the meta pseudo labels, okay? So kind of, there are interactions between student and teacher, okay? And this is the original objective, but there's actually no way to solve this loss function. So what they do is they approximate this. So this could be slightly reduced by getting some gradient for this loss and updating these parameters slightly. Okay, so rather than find the solution that globally minimize this loss function, they find the student parameter that slightly reduce the loss function, loss LU. Okay, by doing this. This is same as the parameter update rule of the gradient descent. Okay, and then they also do this. Okay, for so previously this was the global minima, but rather than that, they use slightly reduced student parameters in this, and then they find the teacher's parameter, then minimize this. Okay. So actually this LL is the cross entropy for the labeled data, okay? So they minimize, they actually one time update the student parameter and then find the teacher parameter that can minimize this cross entropy loss on the labeled data, okay? So by iterating these two steps, this teachers network is also updated. Their parameters are also updated. So the authors are saying that they are getting better than the supervised learning. Okay. So for students, for unlabeled data, they learn the student parameters using the gradient descent. And for the teacher network, for labeled data, they obtain this loss function, okay, using the student parameters. And then they also apply the gradient descent to update their teacher's parameters, okay. By iterating through this, their performance can be better than the pseudo labeling. Okay, meta pseudo labeling is better than the pseudo labeling. Okay. So they are saying that this meta pseudo labeling is better than previous in quantitative measure, and this is some qualitative examples. So actually, there are two classes: the red and green. Okay. So the ground truth red points looks like this, right? And the ground truth green samples are distributed like this, okay? But we are given only three labeled examples, okay? In their paper, they stated like this. So there are, this is the plot for 2,000 examples in two classes, the green and red, okay? If we are given enough data, we may have our supervised model is properly obtained. However, we are given only three labeled examples plus other remaining 2,000 examples, okay? A few thousand anyway. Maybe this amount of examples are unlabeled and only three are labeled, okay? In this case, the color indicated here is the model's boundary. Okay, so actually, this color is indicating that this region is the red region. Okay, so because they only have three labeled examples from this true distribution, they cannot effectively learn the boundaries. Okay. So, I mean, the true boundaries have to be like this. Okay, so the color should be like this. This region have to be red, and this region have to be green. Okay, but here, even for the supervised learning, we cannot get the true regions. Okay, so because only 3 samples are obtained here, maybe, and here, and for here, green samples are obtained, green samples are obtained. So the regions obtained from the supervised learning is wrong, okay? Because we are given only small amount of data. The supervised learning, their result is wrong, actually, okay? But if we use pseudo labels, we can propagate the label information from these 3 samples to remaining unlabeled this number of examples. And by doing that, our boundary here becomes actually better than the supervised learning, okay, compared to supervised learning. So actually, this is the true distribution for red, and this is the true distribution for green, right? Ideally, it have to be like this, but pseudo labels are better than supervised learning here. And the meta-pseudo labels, they are better than the pseudo labeling thing, okay? So these challenges happen for when the labels, for the case when the labels are not enough, okay? Okay. So this is the pseudo, meta-pseudo labels, okay? So are you guys following me? I'm not sure. 이거 혹시 예제 이해했나요? 이거 슈퍼바이즈 러닝이면은 사실은 이게 빨간색 포인트가 정답이고 그린 포인트가 정답이면 이 메타수도 레이블스처럼 이게 색깔 칠한 게 그 모델이 구한 바운더리거든요. 그러면은 메타수도 레이블에 나온 것처럼 빨간색 점들이 몰려 있는 거는 위전을 이제 빨간색으로 칠하고 초록색 점이 몰려 있는 건 초록색으로 칠해야 되는데 이게 2000개 샘플을 구했을 때 이렇게 분포가 이렇다는 걸 아는 거고 2000개를 못 구했고 뭐 예를 들면 3개만 레이블드 된 정답이 있다. 나머지는 다 언레이블드 돼 있다. 이러면은 이게 모양이 이렇다 보니까 좀 구하기 힘들다는 거죠. 그래서 뭐 이쪽에서 하나 뽑아지고 3개인데 레이블 된 게 3개인데 여기서 뽑아지고 여기서 3개를 이렇게 뽑았으면 지금 색칠하는 영역처럼 뭐 이렇게 빨간색이 뭐 이렇게 이쪽 왼쪽에 모여 있고 초록색이 중간에 있고 빨간색이 그 다음에 있는처럼 좀 레이블이 제대로 이렇게 많이 없으니까 잘못 구해지겠죠. 근데 수도 레이블링을 하면 이제 이 3개의 레이블드 된 정보를 가지고 1997개 나머지 언레이블드 된 이그젠플들을 이제 레이블링을 좀 해가지고 그나마 좀 나아지는데 여전히 틀렸죠. 근데 메타 수도 레이블 하면은 잘 프로파게이션 해가지고 좋아진다는 겁니다. 재미난 결과인 것 같아서. And the next thing I want to share with you is the transfer learning. This is also the technique which could be used without the actual data set. Okay. When we do not have much large-scale data set, we can use the pre-trained model, okay, and do some transfer learning. Okay. But I think this transfer learning is it is used in the image classification task. Actually, the AlexNet or VGGNet and also the ResNet, most of the image classification network do the training in the ImageNet dataset and do transfer learning or called as the fine tuning on the small scale dataset. Okay. In that sense, I'm expecting that most of you are already familiar with this transfer learning. Okay. So in this transfer learning, it stores some knowledge gained while solving one problem, and it is reused when solving similar but different problem. Okay. Okay, so the concept is similar to what knowledge distillation or pseudo labeling are doing, but in the sense that the target applications are different. The pre-trained network, they are dealing with similar problem, but their data set is different. Okay, for example, in ImageNet data set, they are solving the ImageNet. The pre-trained networks are trained by the ImageNet data set, but fine-tuned on the different data set. So their application is similar, but different. Okay, but knowledge distillation or pseudo labeling, their application, there's targeted problem between teacher model and student models. They are saying, okay, that's maybe the difference between transfer and other techniques. Okay. Okay. So I think you are already familiar with this kind of thing. So we first train some randomly initialized CNN network using large-scale data, such as the ImageNet dataset. And by fixing some former part, which is hard to train using the small-scale data, and only unfreeze the later part of the network, and train this part using some small-scale but targeted data set. Okay, that's the transfer learning. We somehow accumulate the large scale knowledge, some knowledge accumulated from the large scale data set and fine tuning it to our targeted problem. Okay, that's the transfer learning. So before CNN, this concept was not very popularly used, but nowadays people are doing this frequently because training CNNs from scratch is taking much time. So this technique, transfer learning, is quite popular. Okay. So this is the conceptual figure for this transfer learning, but this is more concrete figures for the transfer learning. So this is the input for the CNN architecture. And actually, this is the AlexNet. And maybe having 8 layers. And F8, some 1, 2, 3, 4, 5, 5 convolutional layers. And we have 3 FC layers in AlexNet, right? So this is the FC, and at the last, because ImageNet data set having 1,000 class, the last output of the this CNN network is having the 1,000 dimensional vector, okay, and input this image, okay. So we have to train this AlexNet using the ImageNet data set, and then we will replace this last layer to fit to our application. So for example, if our application is image classification with 10 classes, then this will have only 10 dimensional output. Okay. So by fixing the other earlier layers, we can unfreeze this last part only and train this part only for the new data set. Okay. That is the transfer learning. And you can actually implement the transfer learning very easily using the PyTorch. So I found that this link is correct, but if you search for PyTorch model zoo in the Google, then you can find how to use the already pre-trained networks in the PyTorch. So PyTorch gives you the easy interface to make the already known architectures, okay, like the image AlexNet or ResNet or Bridge.net. For those kind of famous architectures, you can easily load it from the PyTorch library. So if we search for this model zoo, you can do that. And also, if you want to load the weight, then the PyTorch will also load the ImageNet pre-trained weight for that architecture. Okay, so that's actually implemented here. So using this torch vision, you have to import this, and then you can access the RxNet architecture by calling models.rxnet. And if you set this flag, the pre-trained as true, then you can even load the pre-trained weight. Okay. And if you visualize the network, then it looks like this. Okay. The RxNet architecture and having some convolutional layers in earlier layers, and then it has the FC layers after that. Okay, and you can see in the last FC layer, it gets this dimensional vector as input, and it outputs 1000 dimensional vector as the output. Okay, because it was proposed for the ImageNet dataset having 1000 classes. Okay, you can replace it using this kind of code. Okay, so you can access the last part by this accessor, and you can initialize that part using new FC layer whose output is only 10 dimensional. Okay, if your application is doing the image classification using 10 classes, then you have to change its final output dimension as 10 from 1000, right? So you can do this. Okay, you can access this last layer and reinitialize that. Okay. And also, this requires underbar graph. If this value is false, then that layer will not participate in the training stage. It means their parameters will not be updated using the SGD. Okay, so this is actually meaning you are freezing all the layers inside this architecture and then replace the last layer. Okay, then only the last layer is having this requires underbar graph as true. So if you do this and train using some new data set, then only the last layer will be trained. Okay, this is the transfer learning. Okay, any questions till here? Maybe I'm expecting that most of you are already familiar with this transfer learning. Okay. And the other thing, the other theme actually is the continual learning. And sometimes we call it as the incremental learning. Okay. So actually this incremental or continual learning, we will we will use it for raising the programming assignment too. Okay, so I think you have to pay attention to this, right? Okay. So, is there anyone who already heard about the continual learning here? No, nobody heard about that. continual learning 들어본 적 없네. 들어는 봤고, 그러면 반대로 안 들어본 사람 손 들어보면 다 들겠네. 아니면 그건 또 아닌가? 얼핏은 들어봤을 것 같은데. So this continual learning is meaning that so previously in transfer learning we explained the situation that we train our network on one data set and then we train the same network to another data set. Okay, we explained the situation like that. It frequently happens, right? But when doing that, when trained on one task, And then we train our network on the second task. Many machine learning algorithms forget the previous task. Okay? So this is actually the problem. This is the problem called as catastrophic forgetting. Okay. So anyway, the network forget previous knowledge. Okay. So continual learning is aiming to relieve this phenomenon. Okay, and they are called as lifelong learning or incremental learning. Okay. Okay. So the phenomenon looks like this. So this is the lows, and this is the epochs, and this is in the left side part. We will train the network on data A. Okay, and the right we will train the same network on the data B. Okay, then the loss for A task, it decreases, okay? But loss for task B could be reduced, but mostly flat. It shows the flat graph. Okay. Then the loss function for data from test, maybe validation or testing data from the domain B would be getting smaller, right? Because we are training the data from domain B, right? But this is the problem called as the forgetting. Okay. So after we start train the network for the domain B data, then the knowledge accumulated for domain A is gradually forgetting. So the loss for validation data set in the domain A, their loss is getting higher, okay? After we start training on the data B, okay? Okay, so everyone understand this? Okay. It's not that difficult, okay? So the performance for task A drops as training proceeds with the task B, okay? This is the forgetting. So it is first observed in early 2010s, and this technical report published it in arXiv. They are saying that adding dropout layer is always give us some good trade-off between new task and old task. Okay, so I'm not sure you are able to see this thing. So they constitute the same four combinations of the layers with and without the dropout layer. Okay, and for each pair, if you find their graph, so this graph is SGD using sigmoid, and this green is denoting the same with dropout. Okay. And this is testing error for the new task. And this is the testing error for the old task, okay? So ideally, it should go this direction, okay? Then it means it have low error for both tasks, okay? So if algorithms, their graph goes here, then they have better trade-off between old and new tasks, okay? So, I mean, for each pairs, they are saying if we use the dropout layer in the intermediate layers, their trade-off between old and new tasks are getting better, okay? So this graph goes here when we use the dropout layers in the middle, okay? But this is helpful, but not I mean, more grounded solutions, okay? So after this, people are gradually thinking about how to relieve this forgetting phenomenon, okay? So one solution proposed in this TPAMI 17 is called as learning without forgetting, okay? So actually they propose 4 baselines, okay? This is the original model, and they are trained. This is the image, and this is the old task loss, okay? And they are introducing 4 baselines, okay? So this, when the blocks are not having some color, then it means they are freezed during the training, okay? And when they are colored with blue, these blocks actually means they are tuned, they are learned during the training, okay? They are fine-tuned, okay? And this red blocks, they are saying they are randomly initialized and also participate in the training, okay? So when we do fine-tuning, which is the transfer learning, okay, we fix the earliest layers and then tune the last layers only, okay? This is the fine-tuning. We fix the earlier layers that role as the feature extractor, and then, no, sorry. That is feature extractor, sorry. Fine-tuning, that means they fix the last part of the old tasks, but train these earlier layers. That is called as fine-tuning. In here, they fine-tune the earlier layers, okay? So they call it as the fine-tuning, okay? And this part, the red, is the output for new task, okay? So they fix the last part of the old tasks, but train the earlier layers and also the last layer for the new task, okay? But feature extractor use this earlier part as the feature extraction network, and they freed this for training for the new task, okay? Okay, so this feature extraction baseline means they will fix all the layers except for the last layer when they do continual learning. They do training for only for the new task. Okay, so they are assuming that they already trained the original model for the old task. Okay, and actually this part we are denoting the models for at this epoch, not this epoch, okay? So here, we already trained the original model, right? We already have the model trained for A domain, okay? So that is this, the original model is trained for one task already. And when training for the other task, we will fix, for the fine-tuning baseline, we will fix the last layers for old task, but unfreeze the earlier layers and the last layer for new task, okay? This is the fine-tuning baseline, okay? And for feature extraction baseline, we will fix all other layers, but will train only for the last layer for new task. Only train this for new task. That is the feature extraction baseline. Okay. And joint training, that is looks like this. So that will train all network using the old task data and also the new task data. So, I mean, when fixing this part, they are indicating that they will not use old task data in new task training. Okay. For here, and also here, they will not use old task data, but use only the new task data. This is important, very important thing. But in joint training, it means they will train for new task training. They will also involve old task data. Okay. They will train this using both old and new task data for the joint training. Okay. And the learning without forgetting what they propose, they will also use for old task data, they will not use, but they will use only new task data. Okay. For this BCE, they will not use old task data, but will use only the new task data. But for joint training, they will use both. Okay. Okay. And the result looks like this. So fine tuning and I will omit this, and feature extraction, joint training, learning without forgetting. Okay, this is the thing they propose. Joint training is supplying both old task data and new task data. For new task performance and the old task performance, this is best, even better than learning without forgetting. Okay, but thing is, they are slow because they have to see both old data and the current data. Okay, so their training takes a lot of time. Okay, and also they have to store both old task data and new task data. So their storage requires a lot of memory, maybe, okay, and requires previous task data, okay, yes. So performance-wise, this joint training is best, but in practice, we cannot do joint training, okay? So this learning without forgetting is providing some good trade-off between the good accuracy and efficiency, okay? But fine-tuning and feature extraction, for fine-tuning, it means it trains the earlier layers only for the new task, right? So it forgets the old task knowledge, okay? So it performs good for new task, but it forgets the old task knowledge, so it performs bad for old task, okay? And also in the sense that it only uses the new task data, the training efficiency is good, storage requirement is medium, right? But their performance for old task is getting worse than before because of the forgetting, okay? So when we do fine tuning, we can observe the forgetting phenomenon, okay? And if we use the architecture as the feature extraction network, if we fix all the layers pre-trained by the old task, and if we do not learn for that layers, then the problem is it can retain the old task knowledge. So original task performance is good, but the performance for the new task is not getting better. Okay, so I mean, this is the stream. This is the stream for the performance for the new task. Okay, this is the stream for old task. Okay, these networks are tuned for old tasks and never trained further. Okay, so these features are kind of optimal for old tasks, but not optimal for the new task, and they are not further trained for the new task. Okay, so their accuracy for new task is kind of limited. So that's actually denoted here. Okay, the new task performance is limited, but they can retain the old task performance. But fine tuning, they are good at training the new task, but they forget the old task. Okay. Okay, and duplicating and fine tuning, this is kind of having two networks. Okay, the network for old task, and they duplicate that network and do fine tuning for new task. Okay, their performance is rather good for both old and new task, but testing efficiency that gets bad because they have two networks. Okay, this is also not very optimal case. Okay, so because of this paper is proposing the learning without forgetting scheme. Okay, opposite to joint learning, joint training, they can use only the new task data. Okay, they don't have to see old task data, so their training becomes fast and memory requirement, storage requirement that is good, and also testing efficiency that's good. But and also they relatively have good trade-off between new task performance and the old task performance. Okay, and they don't require to see previous data. Okay, so that's why they say this learning without forgetting is good. So everyone follows this. Okay. So, okay. Maybe you have to use this LWF in your homework, maybe second programming assignment. Okay, and what they do is they have two types of loss functions. Okay, they define the cross entropy loss for old task and at the same time for new task. They can do this. They can do this using ground truth of X in new domain, right? Because in LWF, they are using the new domain data, right? This is the prediction. So they can compare with new domain, their ground truth with their network's prediction, okay? And at the same time, they use the old old rules, but they are not applied to old data set. They are not applied to old data set, but they are applied to new data set. Okay. I already said to you this LWF is not using old data set, but they can still get output from this node. Okay. For new task input, they will get this output. Okay. For old task, right? And they secure their, there's no ground truth for new task data, right? For old task, let's say this is there are old, this is denoting the old task image, old task data's image input. And let's say this is the new task data's image input. Okay. They will have ground truth for new task. Okay. I don't think this is good notation. Say they will have this, the new task data's label. Okay. They will have these pairs, but they will anyways estimate this for this image, okay, using this network, okay. By inputting X new, they can anyways output some output for old task, okay, and we will call this as it, okay. There's no ground truth Y old for this data, right? But here they are saying that they will apply cross entropy laws, okay? What they do is they secure this using original model. Okay, so if they input X new here, then here something is estimated. Okay, we do not know it is ground truth, but they estimate something here, right? And we regard this as the ground truth. And for network which is being trained for new task, this value could be changed, but we actually close this to the original output. Okay, that is actually stated here. Okay, everyone understand this? 좀 헷갈리는 개념이라 가지고 sorry for foreigners, I will summarize it in Korean. So 이게 LWF는 새로운 데이터만 쓰는 거잖아요. 조인트 트레이닝은 둘 다 써서 이거 막 둘 다 학습을 할 수 있는데 LWF는 옛날 타스크 데이터 하나도 안 쓰고 새로운 타스크만 학습하는 건데 로스는 두 개예요. 얘는 뭐 새로운 타스크 데이터로 할 수 있는데 얘를 어떻게 하는지가 애매하잖아요. 근데 얘 그라운드 트루스는 오리지널 모델, 그 새로운 타스크에 학습하기 이전에 프리트레인드 됐던 오리지널 모델에서 나온 출력값, 새로운 뉴 타스크에 대한 영상을 넣어서 얻은 출력값과 새로운 타스크에 막 이렇게 학습이 되면 그 출력값이 막 좀 성능이 안 좋아지겠죠. 그거를 잃지 마라. 이런 로스를 크로스 엔트로피 로스로 걸어주는 겁니다. 이해가 됐으면 좋겠네요. So this is the LWF loss. So actually it is not seeing the old task loss during the training, incremental training, but they can make this old loss using the original model's output and also the model being trained, their output for new data. Okay. So when they do this LWF, they are saying that this is the LWF result, and this is the fine tuning, and this is the feature extraction result, and this is the joint training result. So they are showing only the relative accuracy to this LWF result. And for the fine tuning, this is the different data transfer learning, the continual learning setting. They first train with ImageNet and then further train with VOC. This is the thing for that. Okay, they are using several data set settings, and this is their accuracy for old task. For here, the old task is ImageNet. Okay. And new task is VOC, right? This ImageNet and VOC. Here, ImageNet and CUB is new task, and showing the accuracy for old task and new task. Okay, and they are showing the relative performance to the LWF. So for the fine tuning, they tend to have better accuracy in new tasks compared to the LWF, but have less accuracy to the old task compared to the LWF. But this feature extraction and joint feature extraction, they have better performance for old task, okay, compared to the LWF, but have less accuracy for new task, okay. And joint training, this is best in accuracy, but sometimes less than LWF, okay. So LWF, that can retain the accuracy in both old and new, and at the same time is efficient for training, okay. So this is the same result. And maybe after that, we will continue this, some more schemes for relieving the continual learning, okay? Okay. Maybe in the next week, we will continue this, okay? Thank you for listening, and let's finish today's lecture here, okay? Thank you.